Good afternoon, all. I welcome you all back to the International Conference on Sustainability and New Paradigms in Civil Engineering 2020, organized by Department of Civil Engineering and Department of Construction Technology and Management, the Anand Sagar College of Engineering. Now we shall start our next keynote address.
Good afternoon,
So
all.
we have our speaker, Mr. Kumar Ramaswamy, joining us from New Zealand. Just a brief introduction about our keynote speaker. Kumar Ramaswamy is a principal structural engineer
Welcome you all
at
back
AECOM
to the
Consulting Services
International
Limited
Conference.
on Sustainability and New Paradigms in Civil Engineering 2020, organized by Department of Civil Engineering and Department of Construction Technology and Management, the Anand Sagar College of Engineering. Now we shall start our next keynote address.
Good afternoon,
So
all.
we have our speaker, Mr. Kumar Ramaswamy, joining us from New Zealand. Just a brief introduction about our keynote speaker. Kumar Ramaswamy is a principal structural engineer
Welcome you all
at
back
AECOM
to the
Consulting Services
International
Limited
Conference.
on Sustainability and New Paradigms in Civil Engineering 2020, organized by Department of Civil Engineering and Department of Construction Technology and Management, the Anand Sagar College of Engineering. Now we shall start our next keynote address.
Good afternoon,
So
all.
we have our speaker, Mr. Kumar Ramaswamy, joining us from New Zealand. Just a brief introduction about our keynote speaker. Kumar Ramaswamy is a principal structural engineer
Welcome you all
at
back
AECOM
to the
Consulting Services
International
Limited
Conference.
on Sustainability and New Paradigms in Civil Engineering 2020, organized sorry for the inconvenience. A brief introduction about our keynote speaker, Mr. Kumar Ramaswamy. He is a principal structural engineer at AECOM Consulting Services Limited, Auckland, New Zealand. He is Chartered Professional Engineer, Institution of Professional Engineers New Zealand, and member of Institution of Professional Engineers New Zealand. Kumar Ramaswamy has more than 17 years of experience in the consulting engineering industry in New Zealand. He has worked in some of New Zealand's largest alliance-led projects, which have given him the opportunity to acquire skills to deliver, design multidisciplinary infrastructure-based components, build good client relationships. Kumar has experience in managing work processes and personnel to ensure a deliverable is issued on time and quality assurance requirements are satisfied. Through his project experience, he has successfully managed design teams, sub-consultants, and met deliverable requirements. Kumar is currently working on City Rail Link project leading Bridges team and leading major temporary works design team. Sir, over to you for the keynote address.
Thank you, Megha. I hope you all can hear me now.
Yes, sir.
Okay. Um, Thank you. And I think I got 4 welcomes today because of the technical glitch, but that's pretty good. um,
Sorry.
yeah, that's fine. That's perfectly fine. So I'll just share my screen. If you can confirm, if you can see my screen, that would be great.
Yeah. Yes, the screen is visible.
Thank you. Right. Good afternoon, everyone. Uh, Thanks for the introduction again. My name is Kumar Ramaswamy, working in ACOM, New Zealand. And welcome to the presentation, which is on 007 Rail Bridge Replacement Project, Design and Construction Challenges. Before I start my presentation, I would like to say why I think this presentation is actually aligned with today's conference, because today's conference title is also on sustainability and new paradigms in civil engineering. So this is quite relevant to the project I'm presenting today, because we had used a specific product which is called weathering steel, which is quite sustainable. And one of the key objectives of the project was to sort of make use of existing structures where we could. So, on both fronts, I think the presentation which I'm going to start now is quite relevant to the theme of the conference today. So without due delay, let's get into it. So I'll start the presentation with a brief background on the project, existing bridge conditions, objectives of the project, challenges we faced as a design team, challenges for the construction team, and outcome of the project, and we'll conclude with conclusions. So North Island Mainline Trunk, which in short form is called NIMT, is a main rail corridor, which is between Auckland and Wellington, providing both freight and passenger services. Many of the structures along the corridor were quite old and nearing their end of service life. So in 2011, KiwiRail commissioned ACOM for investigating 30-kilometer section of NIMT line. The main aim of the study was to identify and assess options for improving the operational efficiency and network reliability for the next 50 years. So the main objective was to see whether the structures needed refurbishment, upgradation, or a complete replacement. So the study identified 7 key bridges that required replacement or refurbishment. Um, and the study also identified that those 7 bridges, the age was ranging between 76 to 100 years. So as you can imagine, that needed replacement or refurbishment. So most of the spans, surprisingly, were approaching their end of their working life. In 2013, KiwiRail released a tender for replacing those bridges, along with another bridge, which is called Bridge 273, which was located north of the investigation area. So this was the team. So KiwiRail is the New Zealand's national rail business, similar to Indian Railways, if you like, who manages and develops develops and maintains the national rail network, operates freight and also long distance passenger services between Wellington and other suburban services. ACOM URS, after the merger, ACOM URS teamed up with Downer to deliver this project. And at this point in time, I would like to acknowledge that I've taken permissions from KiwiRail and Downer to present this at this conference. So the bridge locations. So this is the map which shows all the location of the bridge sites. So bridge 201 to 209 are located in this small section. I don't know if you can see my mouse here in the tiny section of in the map. And the additional bridge which was added at a later date was located in between Auckland and Hamilton. Why the name for this project was 007 project. However, that 8th bridge was added at a later date, but we still wanted to call it as 007 because it sounds better. So I'll just show you some of the photos of these existing bridges. You'll be quite surprised how this bridge is actually holding up. So bridge 201 and 203, which is on the top left and right corner, is crossing a river called Ongare River, which has quite a significant catchment area. And the seasonal flood levels are very high compared to the existing rail track. And I've been told, I haven't seen that the water would raise up to the track levels at certain times of the year, which was pretty bad. And bridge 201 also had, if you can see this, you can see 2 concrete piers, which were built in 1980s, which were replaced back then. Sorry, I need to, yeah, sorry. So central piers were introduced to this bridge to enhance the life. And bridge 204 in the lower photo also traverses the stream, and there is a local access road as well. Bridge 206 and 204 also cross a small stream which feeds the river and services a local road as well. So bridge 207 on the right hand corner is a steel viaduct spanning the river. 208 and 209 at the bottom left and right corner, they both traverse again through a small stream and provides private access to some of the properties on the sides of the tracks. All the bridges, if you can notice, had the sleepers directly fastened to the deck spans, with deck spans being a combination of either steel plate girders or steel trusses. The substructures were typically hardwood timber piles or piers, all at the end of their reliable life. So this photo shows a view of bridge 273 in the foreground, and there's a relatively newer bridge which is on the background, which is 272. So this bridge also spans across a stream called Mangawara. Similar to the other bridges, this was also constructed with steel plate girders with sleepers directly fastened to the girders. So the deck was supported on aged timbers, as you can see in the photo there. There was quite a significant scour issues with the, there were quite a significant scour issues with this bridge as well. Okay, so project objectives. So the project scope included both design and construction of 8 replacement bridges, and the construction works were required to be carried out with minimal disruption to the operating rail network. So the objectives included increased reliability of bridges by providing structures designed for ULS seismic effects, and any work would require track closures had to be limited to 24-hour or 48-hour block of line. So typically we had to replace a bridge within 48 hours. For some of the bridges, which was only 24 hours as well. KiwiRail has a policy called fix and forget policy, which means they want minimum maintenance requirements for their structure where feasible. And they also wanted to exclude us from using any timber structures as well, and also replace directly fastened decks with ballast decks as well. So there were two bridges where the existing substructure could be strengthened. Um, so the design approach which URS or ACOM took was, we had to satisfy the project objectives, obviously, and the constraints had to suit the construction methodology of our client as well. This involved developing solutions that could be used across many of the bridges as possible, so that it could be repetitive, and which would minimize any errors on site. It also so the developed solution also had to be usable, in an unfamiliar situation. So we had to come up with some really smart ideas, which I'll go through in a bit detail later. So 6 of the 8 bridges were online replacements and had very limited time, as I mentioned before, which were ranging from 24 to 48-hour block of line. To achieve fix and forget criteria, we adopted weathering steel bridge superstructure with ballasted decks and also reinforced concrete substructures. The ground conditions were pretty horrible in that location because it was susceptible for liquefaction and lateral soil flow as well. So they produced quite a bit of design challenges for the team. And we try to mitigate this by using ground improvement works or designing the structure to withstand the seismic effects as well. Bridge lengths which the design team considered reducing the bridge span where possible by using mechanically stabilized embankments. So what design standards did we use in the design? So we had to use KiwiRail Bridge Design Code, which is our design code in New Zealand. And we had to use ARIMA Manual for Railway Engineering, which is an American standard. And we also had to use NZTA Bridge Manual, which is New Zealand Transport Agency Bridge Manual for the seismic provisions. I forgot to mention that these sites are highly seismically active as well. So in terms of superstructure design, as mentioned, we went with weathering steel. So what is weathering steel? Weathering steel is a high strength, low alloy steel that does not require any additional coating such as galvanizing or thermal zinc spray or any paint system to maintain it. As the steel starts to corrode, it develops a protective surface called patina. Alternate cycles of wetting and drying would help the patina to form. And once this is formed on the surface, it forms as a protective steel for the parent material, which stops from further degradation in terms of corrosion. So weathering steel was well suited for the location, and it does not perform very well in high corrosion zones as marine environments. However, this site was quite inland, so it was pretty good for the location of the site. So the ballast tray is one area where it continuously, there is continuous wetness and abrasion. So that could compromise the formation of patina. So we had to use robust waterproofing membrane only for the deck. The use of weathering steel is actually gaining quite a bit of momentum in New Zealand and Australia. HERA, which is the Heavy Engineering Research Association in New Zealand, has developed a proper guide for us to sort of assist in the design of weathering steel structures now. So the other benefits of using weathering steel was reduced fabrication, as there is no coating required for the steel work, no need to repair the damaged coating during installation. People who are involved with those sort of work will understand how painful it is to sort of repair the protective coating once there is a damage on site. So less whole of life maintenance, as the bridge remains in service and does not need any or very minimum maintenance required. And obviously there is less environmental impact and greater safety for maintenance staff working in the rail corridor. So the other aspect of substructure design was ballasted through girder deck. On ballast deck, the bridges, the sleepers are bedded into the ballast. The ballast is carried by the ballast tray, which is supported by the steel plate girders and cross beams. So the typical cross section adopted with the main girders as shown in the sketch there. So we had to raise the main girders as high as possible, which will give us the construction depth of the superstructure to be minimized between the track level and the soffit of the deck. This also allowed existing rail alignments to be maintained while achieving vertical clearance and freeboard requirements underneath the spans too. This had a significant benefit to the client of being able to replace the existing directly fastened tracks with ballast tracks whilst limiting track realignment works for the approaches. This type of deck system also allowed individual bridge spans to be prefabricated and assembled offline and then lifted or slid into position. This allowed the majority of the construction decks to be undertaken outside the rail corridor, thereby minimizing the effect on rail operations. Deck spans could also be placed during scheduled block-off lines. So this solution is a bit expensive than directly fastened deck, but requires very less to no maintenance on the bridge. The ballast absorbs the dynamic effects of the train loading and accommodates any small changes to the track alignment without affecting the superstructure. It allows the ballast tamping machine to traverse the bridge uninterrupted too. So the support conditions, these bridges were typically supported on elastomeric bearings. This provides a sort of a simply supported end condition which allows for thermal movement of the superstructure. This Tamaranai place is pretty, it's a place where it gets really cold in the night and then it gets really hot in the daytime. So we had to make provisions for thermal movement. Otherwise, the bridge would lock up and create unnecessary design actions, which was not designed for. So we had to make allowance for temperature movements. The ballast tray, which is on the right, the second sketch also sort of cantilevers past the end crossbeam. Sorry. Yeah, so the end crossbeam, and it is supported on a PTFE strip on the ballast retaining wall. In terms of lateral restraint details, the shear keys were provided at the abutments to restrain the bridge in the transverse direction. Longitudinally, brackets were bolted to the underside of the girders. A nominal gap was provided to allow for temperature effects, as I mentioned before, and also to allow for the deflection of the abutment beam due to surcharge loads and creep deflection. At the single span bridges, the bracket was connected to one abutment with a stress bar to minimize deflections and longitudinal train loading, which is a very stringent requirement from ARIMA as well. Under ultimate limit state seismic loading, the gap provided between the bracket and the substructure, closes up, and the bridge behaves as a locked-in structure, and it behaves along with the ground, wherein the superstructure acts as a prop because there is no gap between the substructure and the superstructure. So this gap could be easily reinstated by removing one of the shims that have been provided between the bracket and the pier cap. Sorry, the shims are actually not, it's not very obvious in the photo, but the longitudinal bracket here and the abutment wall, we machined some shims so that, if there is any movement from the superstructure, it could bear onto the abutment beam without any damages to the abutment beam. So in terms of designing the substructure, we had two options. One was to sort of mitigate the risk of liquefaction, and this would have been achieved by cement mass stabilization or with micro hulls, deep soil mixing. We did use this option for some of the sites which were suitable, but not all sites were suitable for this sort of approach. So it was only adopted for 3 of the bridges. And the other option to design the substructure was to sort of incorporate the liquefaction risk, i.e. designing the bridges to be entirely self-supporting and substructure to take all the ULS seismic event loads by itself. So we had to go with deep pile solutions, which was adopted for the rest of the 5 bridges on the project. So the other challenge for the design team was liquefaction. As I said, this is a highly seismically active zone. So the soil, so liquefaction, as you all know, is a phenomena where the soft soil actually liquefies during a ULS seismic event and then puts extra load onto the piles. So the soil actually becomes very soft, it spreads and acts as additional loads onto the piles. And I must admit that this was the governing case for most of the piles in this project. Just to give you a bit of a understanding about soil flow loads, the soil loads were pretty high. So this varied between 4,000 to 6,000 kilonewtons. Bridge 209 was one of the worst affected by the soil flow loads. In order to keep the pile diameters across the project, and the soil flow loads were so big for Bridge 209, we had to get composite actions with the pile casing. So we actually welded some shear studs onto the pile casing to get composite action to meet the demands. So that's pretty innovative stuff the design team come up with, and it was well received by the contractors too in the end. So that's a pretty win-win situation for both designers and contractors, I should say. Dealing with existing substructure, as I mentioned before, there was a strong mandate from KiwiRail that we had to use the existing substructure where possible. So we did use the existing bridge pier on 201. Which I earlier mentioned in the presentation that this bridge had an upgradation done in 1980s. However, the code requirements back then were not stringent. We found with the new code that the shear deficiency for this pier was pretty high. So we had to go for shear strengthening, which we did in the form of PFC beams with threaded rods adjacent to the beam column joint. And we pre-tensioned those stress bars as per NZS 3404, which is our steel bridge design guide. And if you can see in the sketch here, we had to use FRP wrapping at the top of the piles to enhance the ductility of the pier piles, sorry. This was, again, the ductility requirements were not so onerous back in 1980s, but in the recent times, the ductility requirements are pretty onerous, and then we had to provide more confinement in the form of FRP wrapping onto the piles. For Bridge 201, the sketch, the photo on the right-hand side, we designed this bridge as a locked-in bridge. There's this existing central pier. The as-builts of this bridge showed that this was just a mass concrete. There was no reinforcement. So what we did was we made the bridge as a locked-in bridge, so only the abutment takes up all the seismic forces. So the central pier was not accounted for any longitudinal seismic. However, we had to use the central pier for the transverse seismic design. We strengthened the pier by providing skin reinforcement around the pier with epoxy bars. The other challenge we had for one of the other bridges is, as I said, this is a locked-in structure. You could see on the left-hand side, we had pretty embankment up to 2.5 meters. We could achieve locked-in behavior for this bridge. However, on the right-hand side, we had a culvert that was one of the requirements. So that was pretty innovative detailing. We had to come up here with shear blocks so that the longitudinal, seismic forces were taken through the culvert onto the adjacent embankment too. And and we had to ensure that the deflections were good to achieve passive resistance as well. Now, practical challenges during construction, replacement of all the bridges, in 24 to 48-hour block of line. That was the biggest challenge, as you can imagine. It's never easy, with all these bridges. The second challenge during the construction was the remote location of the bridge sites. The nearest concrete batching plant was actually 2 to 3 hours from the site. So any minor changes in the design or during construction caused a lot of heartaches to the contractors. Pretty innovative stuff. We actually assembled the superstructure on site and we slid it transversely. And also you had very little room to move the bridges longitudinally because of the strict requirements as per ARIMA code. And we had to strengthen the soil around the existing structure, which was pretty fragile. So that was a bit of a challenge. The gap between the head wall and the superstructure was very hard to achieve as well. And in some cases, we had to use warm water so that we achieve the required compressive strength pretty quickly because of the 28, 24 or 48 hour so this is a photo sort of to show you the constraints on site. So you can see this is the existing bridge. There is overhead power line. There's a crane sitting here. There's a piling rig next to the existing bridge. So, that's pretty tight. And then it was extremely time consuming because you could only get power off only certain times of the day. So the contractors had to literally wait for 4 hours or 5 hours only to work for half an hour. So it was extremely time consuming. As mentioned earlier, to achieve compressive strength, we had to use warm water in some instances. So the replacement of tracks over earthworks and bridge sections in separate block of line. So that was pretty difficult as well. And then not to mention about the temporary strengthening of the existing bridges, which was pretty difficult as well because the trains were going past those existing bridges every 40 minutes. So yeah, and any changes to the reinforcement or any changes to the track on site caused a lot of delays, and then we had to postpone the actual replacement of the bridge. Now, coming to the more satisfying part. So I'll just take you through some of these bridges, completed bridges. So this is bridge 273, and this is the photo which was taken after the first train went past 273 bridge. And you can see from the other angle, you can see that the patina is actually well formed on the surface. So that's pretty good looking too. The other bridges as bridge 204, which was a complete new bridge. Whereas on the right-hand side is the bridge 203 with the existing or the strengthened central pier with new abutments at either end. And you can see all the patina, which is very well formed. And these photos are pretty old. I think this was taken in 2017. But I've heard that this is prettier now with all the grass and everything, and then the patina is even well formed now. So it's pretty good looking bridges, I must admit. Maybe I'm biased too, but I've been told by other people that they are pretty good bridges too. Right, project outcome. So this project had a number of interesting challenges, as I pointed out earlier, but the design solutions we developed embraced those challenges and allowed the project objectives to be achieved. The bridges were replaced with minimal disruption to the existing rail operations. All block of line scheduled works were undertaken and completed within the required time frame. in a safe and efficient manner. Um, and the Kiwi Rail has confidence that the structures will perform pretty well in the next 100 years with very little or no maintenance. So conclusions. So weathering steel is a very practical solution, and I would say it's a sustainable product as well for low maintenance structures. I must admit it's a fairly new material in the market, but if you use it in the right environment, it provides a low maintenance structure. Steel ballast through girder deck, it's a simple solution, and it can really enhance enhance the spanning ability by minimizing the structural depth. It is also a good solution for the whole of life costs compared to directly fastened decks. No project comes with its own challenges, and we are no exception. But with these challenges also comes innovation. And I would like to thank everyone here today for listening to me. And I would like to acknowledge both Downers and Kiwi Rail for their valuable contributions to this presentation. Lastly, but not least, I would like to thank the organizing committee of this conference for providing me an opportunity to present this paper. Thank you so much. And that's the end of my presentation. If you have any easy questions, and I'm happy to answer.
Thank you, sir. Thank you so much. If any of our participants are having any questions, you can just post it in the chat box. Sir will be happy to answer them. Sir, we have a question from Dr. Neetu Aras. What was the cost of the project?
It's a commercially sensitive question. My apologies. I won't be able to disclose this. Is that okay?
Yeah, sure, sir.
So
Sir,
there
could
are
you
no easy questions then.
regarding the softwares which can be used to analyze these structures, a bridge structure, how to model?
Yeah, so for, it's a, how do I say this? Okay, so we didn't use finite element analysis or anything for this. We used stick models for the superstructure. And for the substructure, we did use a program called STRAP, which is similar to STAD, I guess. It's not what can I say? It's not a finite element analysis or anything. It's just basically stick models we used. And then on some of the bridges, we used response spectrum analysis as well. To answer the question, the structure analysis software was called STRAP, and also for the superstructure, we used Space Gas.
Thank you, sir.
You're welcome.
Thank you, sir. Thank you so much for sharing your work experience. I guess we have not got any other questions in the chat box. So you discussed about the different practical challenges and constraints faced during the construction of these and also strengthening aspects of the bridge. You even mentioned about the solutions adopted to overcome these challenges We are indeed privileged to listen to your talk. I'm sure all of us have benefited from these case studies you have shared with us. Thank you so much, sir. Thank you so much.
Thanks for having me in the conference. It's a real pleasure to be able to present here. Thank you so much.
Thank you, sir. So
Thank
for
you.
all the participants now, we will have a break till 10:40. At 10:45, we shall join again with the same link for the technical session one, which will be shared by Dr. P. chaired by Dr. P. Prakash and Dr. Jyoti TK. So we have the following papers in the first session. Experimental study on bond strength of reinforced cement concrete using M sand under corrosion. Effect of textile sludge in development of new building materials as fly ash bricks. Developing local rubber mixture for seismic base isolation system type HTRB. Static and dynamic analysis of transmission tower with and without cyclonic effects. These four papers will be presented during the technical session one. So it will be followed by the panel discussion. I request all of you to join back by 1:45 p.m. with the same link. Thank you all so much.